Okay. Okay. Hello, everybody. So last week we finished the first part of the lecture, that is collecting the phenomenological inputs, phenomenological data, phenomenological observations, which we now want to use to fuel our deduction of the formalism, right? To complete the theory, right? And yeah, so I just wrote down the titles. Again, this is they mirror sections, subsections. They mirror the convention from the paper. And yeah, let's do it. Let's get into it, because time is of the essence. All right. So okay. So first comment. This is we are building here phenomenological quantum mechanics. So the ideal, perhaps, would be, one could imagine that the ideal would be to build the formalism that uses only the phenomenological elements, only the phenomenological quantities, right? That only those things that we can see will the formalism will build only from the things that we can actually see, measure, touch, and so on and so forth. But that's might be ideal situation, but it's I don't think that most classical theories even can manage to do that thing like this. It's and from what I understand, quantum mechanics for sure doesn't allow that. I mean, there are more things than what we can observe here, directly observe. So it's inevitable that we'll have to introduce some formal elements that are not necessarily phenomenological. For us, if we think about, okay, we want to start building our formalism, so what would be those basic elements that we want to construct our formalism from? And you probably you can kind of guess that based on our discussions of phenomenology, especially the interference experiments, coarse graining and stuff like that, that those nice functions Q that we introduced to parameterize interference in which subsystem interference experiments, as well as standard single system experiments with coarse graining, that those functions might be a good candidate for such a basis of our formalism. So just as a reminder, those are complex valued distributions on a space of pairs of sequences, right? So Q is a function of two sequences rather than one sequence, as it was in the case of standard those phenomenological probability distributions. And so let me see, consult my notes. I had prepared some story here. So right, those functions Q, they were useful for us to simplify what we measure, right? Especially there was this cool pairwise decomposition of interference experiments, right? That we could, we had this experiment where we do coarse grained measurements, right? In our notation, that was this V, if you recall, R, right? And those functions Q allow us to decompose this coarse-grained probability distribution into fine-grained quantities. Right, and the fact that the interference is pairwise is like encoded in the Q being a function of pairs of sequences, not one pair or not four pairs or four sequences or something like that. Specifically two pairs, one pair, sorry, two sequences, which reflects the pairwise interference. There was more bonuses for using Q. We had this factorization rule for independent systems, even if there is some interference between those systems. So, you know, for sure there was, we made some use of those functions, but nevertheless, they are not non-phenomenological quantities. So what I mean that they are non-phenomenological, so a thing would be phenomenological if it would either be directly measurable, like probabilities, or could be like expressed through directly measurable quantities, right? So in case of those functions Q, there are only precious few examples, precious few cases when you can do such a thing. So one of those cases is, okay, so Q is non-phenomenological. Except for two cases. So case number one is if you take the diagonal values of Q, that is if you take the same sequence in both arguments, right? This is supposed to be the probability. Multi-time probability distribution, right? And the probability is measurable as phenomenological quantity. Diagonal part of Q then is also phenomenological quantity. And the second case is when you do double slit experiments, but only there is one barrier. Okay, so there's only one interference event. So then, and then it's not really the whole Q that you can recover, but only the real part of Q. So you take Q Fn. Where do I have it? Okay. Fn Tn. Fn, and let's say the double slit was inserted in at time Tj. So all the arguments are you know, it's almost diagonal except for the jth, the arguments number j, where there is a f plus on one side, f minus on the other side. And this guy, it can be expressed as 1/2 of P Fn, Fj is coarse-grained, F1. And it's a simple pairwise coarse-graining. And you subtract fine-grained measurements.
How did this part where we have a difference, plus and minus two options. This is, let's say, the point where I have this the measurement with this interference, let's say, opportunity.
Yes. So this describes, so you're doing a measurements, and at time tj you deploy coarse grain device, which has two values, two alternatives. It grains over two values. Okay, so this is like the elementary bit, right? So if there were k slits, more coarse grain, you could always express it through those pairwise coarse grainers. Okay, but this is something you can get from experiment, right? Those guys. Okay. So those are the only two cases where Q can be, value of Q can be like expressed through purely phenomenological quantities. So, and now contrast this with oh, sorry, still haven't finished. Okay. Right. Okay, so let's contrast this bare Q with something that I would call symmetrized Q. Symmetrized Q, which I will denote as S acting on Q. Symmetrization Q. It will be a function of not of two sequences, but of n pairs of alternatives. Minus. Okay, so it's symmetrized. So we want to take Q's, okay, and we want to make out of them a quantity that is symmetric, because Q is Hermitian, if you recall, right? If you exchange the one sequence with another, exchange its arguments, you get a complex conjugate. Okay, it's Hermitian, and the real part of Q is symmetric. And then the imaginary part is anti-symmetric, right, with respect to this exchange of arguments. And now we take Q and want to make out of it a quantity that's symmetric, that's more symmetric. It's symmetric with respect to each pair, like here. So if I exchange Fn plus with Fn minus, I get the same value, and it goes for each and every pair. So the procedure is pretty standard in such a way. Just have to take your Q's for different arguments and add them up. And if you add enough terms, you will get the whole sum that has those symmetry properties as we want. So I have here a formula how you can write this symmetrization succinctly, and bear with me. So the formula is like you take a product and you take sums. Sums go over phi j plus phi j minus over pairs belonging to special set, which I call S of fj plus fj minus. So S takes the set and permutations. This is a set of permutations of a given set of the argument sets. So for example, if I take S of like a plus minus, this spits out for me fj plus, fj minus, and fj minus, fj plus. Okay. All right. And if it's you have two identical pairs, I mean two identical elements, it just will split for you. Okay, only one bit. All right. So you sum over all those, permutations of each pair, and the things you sum are Qs. And F1 plus Yn minus Y1 minus. Okay. So such a sum is a function that's symmetric in each pair at each point in time, not just whole sequences, but each individual pair. Okay. And those functions SQ, they are phenomenological, as it turns out. Okay, each one of them can be expressed through some combination of measurable probability distributions. And I won't be writing them down here, but I will flash hopefully I won't break the Zoom by doing this. Here is so for example, if you take SQ where you have, almost diagonal except for two pairs. Okay, so at J you have F plus, F minus, and at K. This thing equals sum of two real parts of Q, which you can see the differences. Here you have J plus, K plus, J minus, K minus, and here you have J plus, K minus, J minus, K plus, this combination. And this thing, this sum, can be expressed through this horror of terms, but each one of them is a measurable probability distribution, okay? Just strategically, you apply strategically coarse grainings, but this is all phenomenological stuff. And it also like shows why you cannot express Q directly through combinations, because there is like, there is more symmetries than Qs possess. Okay.
Additionally symmetrize it.
Yeah. Just to show what you have to do to get completely phenomenological, quantity. But this, and of course, maybe it's not so obvious, but you can use those SQs to also obtain this pairwise interference decomposition. Okay, so let me go back to. Forgot to show this as well. So we see a lot of writing, but if you are very patient, you can show it directly. So on one hand, we have a decomposition in terms of Qs, which we know, which we like, but now you can juggle the sums, introduce dummy variables, and you can rewrite it to be a decomposition in terms of SQs. Okay, so Q can fulfill this purpose of giving us this pairwise decomposition, but SQ can also give us this pairwise decomposition, but in more complicated way. That's true, but it has an upside of being fully phenomenological quantity. Okay, so now, having showed you that, here is a conundrum. Here is a problem we need to address. If we want to, or we need to introduce some formal elements to our along our deduction, right? Then what is the, and they come in kind of ad hoc, right? Because this Q parameterization with Q, we just introduce it because we felt that it will simplify things. This SQ is, it's kind of derived from Q anyway, so it's also kind of ad hoc, introduced ad hoc-ish. What are the standards? I mean, this kind of thing that we add something to purely phenomenological description, right? We need to have some standards for doing this, okay? So what are what are those standards for us to decide whether adding some new formal element is too much or it's just right, okay? So what are the standards to decide if we can go with Q or maybe it's better to go with SQ, okay? We need to define for ourselves those standards. And the criteria we came up with, and I think they are kind of reasonable. So there are two conditions. And you know what? I will come back to the file again because I don't need to write it down, right? Again and again. So we have two points, okay? So point number one, okay? There must be a compelling case demonstrating why the purpose of this new element that we are introducing, new formal element like Q, cannot be fulfilled by phenomenological elements. Okay, so for example, in our case, that would be piece or SQ, maybe. So that's one. So it has to be necessary, right, to introduce it. There has to be a real need to doing that. So not just coming up with whatever, you have to have some reason to introduce it, okay?
This really isn't just a simplicity, because to some extent I believe maybe that you could do it at this level of measured things, but then those formulas, as you have there, who something equals of probabilities. Yeah, but this is a need, but it's not necessarily the need. It's
you see, so this is, you have to make a judgment call here. I would say that the simplicity is a compelling argument, right? Because if you parameterize something correctly, let's say, you can see the structure, okay, which would be obfuscated by if you write everything down with purely phonological stuff. So this is a good argument, I would say. This simplicity is a good argument. But there is a second part, second condition. Even if such a case is successfully made, so you argued successfully that you need something new, minimal extensions of phenomenological elements should be preferred over formulations that introduce additional, potentially excessive complexity. So you have to need something, but still you have to keep it simple. Keep it as close to phenomenology as possible, okay? So these sounds like reasonable asks, okay? Because, we could solve a lot of problems with introducing 10 layers of abstraction with some quantum states and whatever, but maybe those things, maybe they would give us simplify stuff, expose some structures, but maybe they are just too complicated in a sense that you could reduce it, get rid of it, get a couple of levels lower on your hierarchy of abstraction and still get the same simplicity, same structure would be exposed, but you don't have this excess, extravagant complexity. So you have to need to you really need to have a need to introduce something new, something formal, some formal stuff, but it must be simple. The simplest, the better. The more simple, the better. Okay, and I think that functions Q fulfill those two conditions, and let me explain why. Okay, So first, the need. So first, we have the simplification from having this pairwise decomposition, okay? So the structure pairwiseness is, I mean, this is why we introduced those functions in the first place, right? Because the purely phenomenological observation was just the composition into pairwise interference was through some complicated recurrence rule. Okay, so if you wanted to carry out this recurrence rule to completion for n sequence of n coarse-grained measurements, that would be just humongous expression that contains like tens of different species of probability distributions coming from different measurements with different constrainings and stuff like that. It's very complicated. This Q allows us to substitute all of this. Essentially, we're reducing coarse graining as a concept in some way, right? Because everything that's coarse grained can be reduced to something that's fine grained, but at the expense of having this function Q introduced. Okay, so that will be one argument. This simplification, but more than that, because it also exposes the structure, the pairwiseness, because dependence on two sequences. Okay, it encodes pairwiseness of interference into its very structure. Okay, but this is not enough because SQ, I already showed it to you. It also gives us the composition. Maybe it's not as slick, not as tidy, but still, there is pairwise. Pairwiseness is also exposed. It also reduces the coarse graining in this sense. Okay, so this is not enough, but there is more because Q also follow the factorization rule, which we discovered, derived it on when we investigated, interference experiments on independent systems. And this only with Q we can see explicitly this factorization rule. It's completely obfuscated if you're not using Q. If you're just using P's, or even if you try to use SQs, even it was possible to use SQs there, they wouldn't give you this factorization. You wouldn't see it. Okay, and this factorization is pretty important because if you don't have factorization for distributions, then you don't have any way to describe independent systems. If you can do that, you cannot have isolated systems. That is systems independent of everything else. If you don't have isolated systems, then every scenario would have to incorporate descriptions of whole universe, which would completely, trash the whole attempt at doing some formalism here. Okay, so this is something that only Q can do. And more than that, there's another argument why Q is better than SQ, for example, is SQ, because it symmetrizes Qs, it automatically gets rid of the antisymmetric part of Q, that is its imaginary part. If you remember from our discussion on these independent systems, this imaginary part was necessary actually to complete the description. So SQs cannot fully describe this which subsystem interference, okay, for independent systems. It's just incapable of doing that. You would have to introduce another something complementary to it, right? That would account for this imaginary part of Q. So Q is actually the thing that fulfills the needs that no phenomenological quantity that we know of, at least at this moment, that can fulfill. Okay, so it's needed. So the case for being needed, I think, is made with this journey we went through. It kind of showcases that it is needed. Okay, but now is it the simplest thing you can do? And again, I think I can argue that it is the simplest thing you can do. So in what sense it is simplest? Simplest extension of phenomenological stuff. So the probability distributions, right? P's. So P Fn, okay. So this is a distribution on space of sequences, okay? Single sequence. It's a probability distribution. The probability is like, extra bit, but it's a distribution on space of sequences. So what is the most natural and the simplest progression from that formally? Well, you have distribution on space of sequences. So the next thing on the line would be a distribution, not necessarily probability distribution, on pairs of sequences, right? That's the simplest thing you can do. So going from P, that's, where is my gap? Okay, that's dist on space of sequences. And we go from this to Q, which is dist distribution, not probability distribution, but still distribution. You can have measures that are complex value. No, there is no problem with that. On space of two sequences. Right, that's the simplest thing you can do. So if you take SQ, the symmetrized guy, right, it is because of its symmetries, it's a function of n pairs, okay? And the function of n pairs translates into function of up to n sequences. Right? Because, SQ is formed as a combination of Qs, of bunch of Qs, right? So if you try to figure out how many unique sequences you have to involve in this SQ, it's up to n, okay? Which is like, I guess, the maximal value, the maximal amount you can figure out if you have sequences of n of length n. So SQ would represent something it's the most extreme complication on top of P, okay? So, and Q is is the simplest in this sense, from 1 to 2.
Just from the fact that phenomenologically we know that these interferences are pairwise, so actually we do not have to go for something more than pairwise. It's like you can, but these are not needed from the form of formalism. They completely should cover the physics.
Well, but you see, the pairwiseness you could capture it with SQ, yes. Okay, because there is pairs of alternatives. Okay,
yeah, of course, but
but if you SQ would be more complex, more complicated than Q, right? So you could pairwiseness by focusing on each individual timing, right? Or you could go more global for whole sequences. The whole sequences is the simplest choice, right? So it's so we have criteria and we can confront it. Of course, you can argue with that if you want, right? Maybe the argument for necessity is not convincing for you. Maybe for simplicity is also not convincing. But I just want to make a remark here that arguments so far, I'm focusing on very tiny sliver of actually phenomenological observations we made, right? Because you have to remember that there are more observations. We have to synchronize everything, and but that's why it's a deduction. So you have to really comprehend what's going on, you have to keep all those things at the same time in your head. It's difficult to talk about it, but we will see, choosing Q won't betray us, okay? I think those arguments I presented already are pretty compelling, why it's okay. It's not super ad hoc to introduce them. There are reasons, there are good reasons. This is probably the simplest choice you can make here. But when we become going deeper and deeper, we will see that it's still works, doesn't blow up in our face. It will the proof of the pudding will be in the eating. Okay, so it seems to be really good choice, and it doesn't like violate this ethos of phenomenological quantum mechanics, right? We still as close to phenomenology as possible, but we just need to introduce some formal elements that are non-phenomenological. Okay, it's just a pipe dream to think that you can have something practical that's purely phenomenological. Okay, so this is the best. I think this is the best and simplest thing we can do at this stage. Okay. All right, so that's yes, it's kind of yeah. I mean, how I presented it, there was some narrative reasons, but
when you need
it's
when you need to present three offers for a job, someone going to publish show that the only one is the best one that you actually have.
Yeah, I mean, okay, you could argue that I tailored those criteria to fit Q specifically, right? I mean, they're reasonable, necessary and simple. That's very reasonable, okay? But you can have your own approach if you want. Just, you have to, if you build your approach differently, you have different criteria, different methodologies, you have to carry it out to the end, right? And let's see where you get eventually. Will you get to the completion? You get your formalism or not? Because this is the standard you would be comparing yourself to. Because I hopefully will show you the complete journey, right? So, but still you have to explain why you're doing stuff, or if you don't have like criteria, don't have like underlying reasoning, then you could do whatever. You can do whatever, right? But I want to have something that's falsifiable, okay? That you could argue against if you want, but prepare for if you want to argue against, you have to be prepared for bloody battle, okay? Because there will be sharp arguments flying around. Okay, okay, so having that, we can go to the next section. B probability distributions. Okay, so I will start this section, then we make a break at the strategic point, and continue from that.
And the cliffhanger, of course.
Yeah, exactly. All right, so now if we agree to use functions Q as this basic element for our formalism, right? The thing that will be deducing on, I don't know how to say. So we introduce our Qs, we will use them to carry on forward, right? Then, so if you agree to do that, then the next step would be to basically like collate all the information we gathered so far, all the observations, all the consequences of those observations, and we have to make sure that those functions Q are not, don't introduce some contradictions. Okay, so
this is this famous master object, yes, for now.
Yeah, well, we'll see. Hopefully, at the end, we'll have master object. At least some hint of master object.
So this is because we were picking the basis you called it in this subsection. I thought,
it's not basis of vector space, okay?
Yes, it's the basis, like the ground for
Yeah,
for
yeah,
building, yeah. So
yeah, yeah.
the best object for building, but it's not yet the master object. So
Yeah,
the
but
one from which you deduce everything.
yeah, we have those cues, and they have like couple of properties so far. Right? They have to Hermitian, they are Hermitian, and they have this property that they reduce the coarse graining, and that's all we and factorize. Okay, that's all we have. But they surely have some properties, right? They're more than those couple properties, right? And so we have to make sure that we have those cues, figure out what are those properties, and make sure that there are no contradictions. Let's say one observation to be explained would require Q to be ble, but there is another observation that would require that Q is non-ble. Then you have, okay, so that's just completely falsifies everything. Q is no good. Okay. So like the most straightforward way to do this not synchronization, but this making sure of the consistency of cues would be to, okay, if we are just stupid machine, okay, then the thing we would do, we would essentially take all the phenomenological observations that we made and convert them into like equality constraints for cues. Okay, so we will take all the probabilities that we get from all the experiments we can come up with, and we would then treat them as a given parameters. Okay, and we form a system, probably infinite system of equations where Q's would be unknowns and those probabilities would be a given parameters, right? So that would be a collection, a system of equality constraints. So for example, equality constraints. Examples.
And these constraints we all follow from the span of something observation from 1 to 9, which we can.
Or anything else you can come up with. But those that we made are the for sure are the first thing we should do. So examples to give you just what I'm talking about. So you would take let's say 3 fn tn fn. So that would be unknown minus p f t n. So that would be a given parameter from experiments equals 0. So that would be one constraint. So which would mean that the diagonal part of Q is equals probabilities. So that would be one constraint. Another constraint would be
can we put the numbers? Or not necessarily.
It's just examples, but okay, 1, 2. Of course, it's not only one because for every choice of sequence times, it's already infinite number of constraints. But another one would be, you take the sum omega f coarse grained Q n fn plus fn minus p n coarse grained tn v omega coarse grained n equals 0. That will be a second class of constraints, right? So that's a decomposition, pairwise decomposition, right? And you can continue. And it's like for every possible combination, choice of Fs, capital level devices, of values of results, of timings. So if we're a stupid machine, and the most straightforward, the straightforward way to like make queues, functions queue consistent with everything would be just to make up this infinite system of equations, okay? And now, but this is not very productive, okay? Not only that, because if we could solve this system of equation, okay, then that would mean that queues are phenomenological, okay? Because then every value of q could be expressed through known parameters, which are probability distributions. But we know that's impossible. We already know. We know they are non-phenomenological. So we cannot solve this system of equations. So if this was the approach we chose, then this infinite system of equations, of constraints, would be our definition of Qs. Okay? So we would have to carry in memory all those conditions all the time, right? Whenever we write down Q, we have to confront it with all those conditions, right? Make sure that there are no contradictions. And that's just, a lot of complexity, probably unnecessary complexity. So if this was the approach we chose, that would violate this second criteria for introducing ad hoc elements. There is most likely too much complexity, okay? So this is no good. So what is the alternative of doing that?
Yes, because I'm not sure what you exactly mean by saying that they are non-phenomenological. So saying, let's say, dumbly thought that this slightly like with some auxiliary objects like potentials in physics, that they are not physical necessarily. However, they are just useful to calculate observed values of things. And they have some extra degree of freedom, and that's why we call them that they are not physical, because they are not uniquely specified, so they are not phenomenological in the sense, but everything what they're defined as phenomenological and nothing. Whatever else they have inside them is actually a degree of freedom, and you can choose it just up to your convenience. In this sense.
Well, that's gauge invariance is it's not always have gauge invariance, but sometimes you do. But yeah, this is actually this is a good analogy with what you are, because we already know vector potential, for example, could be thought of as a formal element that's not phenomenological, but still, you can derive phenomenological stuff from it, of course. Like from Q, you can derive phenomenological stuff from Q, but phenomenological stuff alone cannot fully, if you would form this kind of system of constraining equations for vector potential, it would be under, like in case of Qs, it would be under, how do you say it? Under not enough information to completely solve it, okay? To have one single unique solution, okay? There are a lot of solutions possible with this system of equation. And it's for vector potential. And I'm arguing now that the same thing is for Q. So vector potential is non-phenomenological like Q, or Q is non-phenomenological like vector potential. Gauge invariance, do Q have gauge invariance? We will see. It's not a given that there is some gauge invariance in your theory, even if you have non-phenomenological stuff in it.
Because I just think that if there is no gauge invariance, then this is just a function of all measured values, like, of all phenomenological some quantities. So it's just a
this is a strong statement you are giving now. I don't know if this is true. It might be true. It sounds kind of reasonable that if it's you have non-phenomenological stuff, so like, the constraining equations are under defined.
If it is not, if there is something that is not phenomenological, so there has to be some extra degree of freedom, and it has to be unphysical by construction, because if it is physical,
I wouldn't use physical, non-physical.
Like it's physical, but maybe better not defined by observation.
Just phenomenological, I would say. That's completely fine. Physical, non-physical is just, I don't know what it means.
Yeah.
But what you mean, I think it's phenomenological, actually. Right?
Yes. In this sense, yeah.
Well, that might be true. That this is there is that maybe
should be free.
Maybe we'll see. Maybe we come back to this. Come back to this later, and we'll get the answer. I mean, this is this is interesting point about gauging variance in such scenarios. There might be something deep in this. So thanks for that. Okay, but if you cannot, you have this situation like this, right? Like we are talking about. So rather than keeping the infinite system of constraints as your definition, which is completely impractical, completely over complicated, that violates all the reasonable rules of anything, what's the alternative? So the alternative, again, is of course something very reasonable. Rather than trying to solve all those equations, constraining equations, we should make an attempt to figure out like some minimal set of properties for Qs that are sufficient for those Qs to be solution to this system of constraints, okay? So some minimal reasonable set of properties for Q that would not contradict those constraints while not necessarily being possible to actually solve. So sufficient but not necessary conditions, okay? That should be enough. So if a sum of Qs, if we define a property for Q that would imply that the sum of Qs is a positive number between 0 and 1, okay, so this sum could represent some probability distribution. So it would be sufficient for it to, to satisfy this kind of constraint. You wouldn't be able to solve this constraint, but at least you're not violating any observation. Okay, and so this is the path we have to choose essentially, right? If we can figure out this minimal set that's reasonable, that reduces complexity for sure, and and basically defines what is the path forward, okay? And now, but of course, the question is how do you come up with this kind of set of properties, right? Well, I would be lying to you if there was an instruction how to do it in every case of every theory of every attempt you are making. But there is some. Well, if you combine all the experiences you had with all this stuff, and on top of that, add this additional thing that we already figure out that Qs, so distributions on pairs on bi sequences, is like the simplest, the more straightforward extension of probability distributions on single sequences. Then you could okay, so what probabilities has some properties, for example, non-negativity, normalization, stuff like that, how those properties would then translate into complex value distributions on pairs of sequences, okay? So if you use this kind of mnemotechnic, this kind of eases the problem for figuring out those the properties. And now we will take a couple of minutes of break. And after the break, I will write down the. No, I won't be trying to present a logical way to, like, get from 0 to all those properties. I will just write them down and then explain what they do. Okay. So break now, 5 minutes. Then we're back into deduction. Okay.
Isn't it so that actually you try to rewrite the constraints in terms of these properties, hoping for simplification that thousands of constraints and just few properties, and well, this is just the equivalence.
Yeah, this is the equivalence. See, this is the idea, but if you wanted to have equivalence, that's too difficult. Okay, you wouldn't be able to do it. We will be happy in implication.
Properties for some extra constraints actually, which wouldn't say spoil the physics, however, would reduce the generality or the freedom maybe of Q that they may have, but they will be just very inconvenient to use.
Yes, so this is what will happen. So there will be, let's say, potentially too much properties. The smaller, smaller number of, not number, but different properties, maybe less elegant properties, would be enough to satisfy all the equations. But but we are accepting the risk that we might introduce a little bit too much. At least, maybe too much. We're not sure. Perhaps when you confront it with everything that you can come up with every constraint you can come up with from some phenomenological observations, maybe you will actually find that it's actually equivalence. But that's difficult to prove. Okay, because we cannot prove it mathematically. We just have to accept that we might, we just have sufficient conditions, and we just have to live with it. So we are, in some sense, we are sacrificing some efficiency, in a sense that you have too much stuff to do the job, but we, in exchange for better structure. Okay. When you make stuff more fragile, more fine-tuned, that's what they call efficiency. It's not a good thing.
So I don't remember that there was something like this, for example, do not need permissivity sometimes, but then you would have to redefine everything, but you do not gain anything, you just got rid of this constraint of permissivity just on the let's say expense of way complicating everything because you have left and right.
Yeah,
which
yes.
were not actually useful for this case. For example,
that's a good way to think about it, I think. Let us carry on. So the list of properties. How do you want to call? Okay, so properties. Properties of Qs. And there will be 5 properties. So I have the list, and I will write them down for you. So I will be numbering them with Q number. So Q1, property Q1, which we can entitle normalization. And it reads that you take a sum over both sequences of your Q and when you sum everything, it's identity. Okay. So this is like a straightforward generalization of normalization of probability distribution. Okay. Okay. On its own, on its own, it's not really connected to any specific observation we made, but you know, there will be 5 properties, and they all work in, they support each other. But you know, how would you come up with this this Q1? Well, this is what you would imagine the generalization of normalization of probability distribution should look like. So then we have the second Q2. It's called causality. Causality.
Could have lived without causality.
Yeah, you know, you have to specify. I mean, the causality was a pretty big deal. First phenomenological observation. And the causality property, I think that the easiest way to write it, that it's Q, any Q is proportional to delta Fn plus Fn minus, which is no vectors. Okay, so it means that we have 2 sequences, but the end arguments, the sequences meet at the end. Okay. Or in other words, if you take Q of 2 sequences where they don't meet, it's 0. Okay. So this is how you can write it. And again, this thing, causality, this is of course not, you cannot come up with some generalization of single sequence probability distribution, right? But again, in conjunction with other properties, which I didn't write yet, its main purpose is to actually take care of observation 1 causality we made in the very beginning. Okay. Q3 is a factorization rule. Factorization rule for independent subsystems. So this is just a repeat of our findings from this lecture where we talk about which subsystem experiments. Okay. I guess this should be as a property. An minus, right, times QB, Bn plus, Bn minus. So factorization rule. Q4 is this one is a doozy. Positive semi-definiteness. definite. And Jesus, you write it like that, really? So positive semi-definiteness, as you can imagine, this has something to do with generalizing positivity of probability distributions, right? But you have complex function, complex values of pairs of arguments. How do you generalize non-negativity of a function? Well, that's positive semi-definiteness. And it's so it's formally you write it as this. So, I mean, there are a lot of ways to express it, but the most most universal way, I guess, it's this. So you take sum, you have here z plus, you have q. There are many ways to express this, the same idea. This is one of them. Gf minus conjugate is non-negative, where z is a arbitrary function of sequences. Two complex numbers. So this is like a a scalar product, right? So you sandwich Q with Z and Z complex valued. Take a scalar product, and this should be non-negative. That's one way of saying this. Yeah, arbitrary function. It's like you have a positive operator.
This is so-called operator.
You recall this is like for operators. You would write it like this, and actually you can word this property differently. So if you take Q, this Q, okay, and just treat it as a matrix where the sequences are like indices, okay, then this matrix is a positive semi-definite matrix. So its eigenvalues are, it's also Hermitian, so its eigenvalues are or non-negative. Okay, if you want to say it differently. So positive semi-definiteness. So this you can view it as a generalization of positivity of distributions, probability distributions. And there is a final property. This one is the most interesting. By consistency. Not consistent, consistency. Consistency. So by consistency is you take your Q and now you pick one of the timings and you sum over, say, J. And you sum over J's arguments, but independently in one sequence and the other sequence, okay? And when you do this marginalization, you get Q for shorter sequences. So this is, of course, the most straightforward generalization of Kolmogorov consistency of, so this is, of course, the most straightforward generalization of Kolmogorov consistency of, so this is, of course, the most straightforward generalization of Kolmogorov consistency of, classical probabilities, right? So you have theories with a trajectory picture. Then you have the Kolmogorov consistency, right? You marginalize over point in time, you get a shorter probability for shorter sequence, right? And we know that for quantum probabilities, that was observation number 2, I think. Yeah, it was 2. They are inconsistent, right? The probabilities are inconsistent. But Qs are kind of consistent, are more than consistent, they're bi-consistent. And this Q5, on top of being this.
But what does it mean? Because
give me a sec. So on top of that being the simplest generalization of consistency condition, it's a sufficient condition to fulfill observation 3. Observation 3, if you recall, was you do the extreme coarse graining, right? So if you take a coarse grain device that's so coarse grained that it actually cannot resolve anything, applying it is the same as not doing the measurement, right? So bi-consistency is a sufficient condition for getting this observation. But there's more, because now you start to combining all those properties. So you combine bi-consistency with normalization and with causality, Q2. This is what explains you the observation 1, causality for probabilities. When you marginalize over the last argument and you get the shorter one, which tells us that there is a causal structure in our theory, okay? The factorization rule, there's nothing special about it. Positive semi-definiteness, this is like the workhorse property, because now when you start combining this, so you take positive semi-definiteness and which one? And normalization Q1 and causality Q3. Take those guys. Those 3 guys. So Q1 plus Q2 plus Q3. Right? This is those 3. They imply that diagonal parts. Positive semi-definiteness already enforces hermicity. Okay, so the real part is symmetric, imaginary part is anti-symmetric. Then on top of that, those 3 guys, they give you that diagonal of Q. 5 is equal to its real part, and it's non-negative. Okay, this is what comes from those guys. And moreover, when you sum, this is 1. Okay, so you combine those guys, you get that diagonal parts are positive and normalize. So those 3 guys tell you that the diagonal part of Q can serve as a probability distribution. Okay, and from positive semi-definiteness, you can also it also implies the decomposition. The sum. If you take bunch of resolutions and you take this, okay, so all those guys also give you that this is non-negative and normalize, and if you sum over fn bars on top of that, it gives you 1. So it's also those 3 guys give you the give you that the pairwise decomposition. Sorry, I stuttered a bit too much, but there's more. So we know the diagonal part is a probability, okay, but now you add or other properties, especially by consistency, and you get that those diagonal parts are also not only it can be a probability, but a probability that satisfies observation one, so consistency, so marginalization of the last gives you the shorter one, but it also it gives you observation two, a violation of consistency condition. Okay, so and this one is actually interesting because from by consistency, so from Q5. So Q5 tells you that you sum over plus minus take Q, right? And it gives you a Q that's shorter. So let me write it like this. Fj minus, right? And this gives you, where is it? So from this you can immediately guess that if you take F, so diagonal part, yen, no, different, sorry. Fj, Tj, T1, minus marginalization. So if there was consistency, there would be zero here, right? Okay, if those probabilities satisfy consistency condition, the marginalize equals the shorter one, so that would be zero. But we know it's not zero. But now using this by consistency, we can actually calculate this reminder. We know what it is. And this reminder is you take sum over Fj plus that is different than Fj minus. You take Q, Fj plus, F1, Fn, Fj minus, F1. Okay. And you can figure just, by consistency, this guy, right? It works. You can have whatever you want, the arguments you are not summing over, right? So in particular, you can take them to be pluses equal minuses, right? So then on the right-hand side, then so if you take all the other arguments except for J, you take to be equal, that gives you probability. So it gives you this guy. It gives you this guy, okay. And on the left-hand side, you take the diagonal part, move it to right-hand side. So this gives you this, all right. And what is left is this. So this is how you get this. So you violate consistency condition, so you don't have trajectory picture because of by consistency, essentially, because of Q. The Q, which quantifies interference, is what's responsible for violating consistency condition for probabilities. That's why you don't have trajectory picture, because you have two trajectories essentially. Okay. And what else do you want to say here? Yeah, okay. So this was a like chaotic rundown of so this is a 5 properties, okay, which much less than the infinite number of constraints. Okay, it's much less. They are pretty neat, pretty simple, if you think about it. They are sufficient to satisfy all the observations we made so far. Okay, so I just gave you a chaotic random how they do it, how they achieve this, and again they are pretty simple and they define the properties of Q. And now, in literature, functions Q that satisfy those 5 properties are called bi-probability distributions. When I say in literature, I mean in literature that we produce. Okay, there is another name that you can, there's also decoherence functional, this kind of functions that share those properties in, let's say they share those properties. Other people call them decoherence functionals, but it's it should be outmoded name. I mean, it's they might look similar, but they are fundamentally different objects. Okay, so it's better to have a new name. Using decoherence functionals has too much history behind it that's completely inadequate for not fitting B probabilities. Okay, so from now on, Q's are B probability distributions. Okay, and we have only 15 minutes left, which is a shame, but at least I will tease the next bit, because so we have our the basis elements of the formalism which we are trying to deduce. Okay, so we'll be working with P probabilities. We have those properties which are neat. Okay, and we can already start to do some big fat conclusions. Okay, and the first conclusion that we will draw right now, I mean right now, like next week already, will be we will already write down the title. It's a big title. Okay, it's a evocative title. The bi-trajectory picture. Okay, so classical physics is a single trajectory physics. Okay, single trajectory picture. It's all built around this. Okay, everything we know about classical physics can be derived from the fact that the master objects of each of those theories, some kind of distribution, probability distribution, space of trajectories. Okay, everything else follows. And now the B consistency here, okay, it's responsible for violating, for negating trajectory picture in quantum mechanics from what we saw, but still those by probabilities they retain this idea of consistency, but instead of for one sequence, now for 2 sequences, right? So a natural question would be, I mean, for me, it was natural. I mean, I don't know if for you it would be natural. So if consistency in classical theories, consistency relation implies trajectory picture, that is, there exists if those multi-time probabilities are consistent, then it follows that there exists a master probability distribution space of trajectories, okay? And those multi-time probabilities are simply restrictions of those trajectories, samplings of those trajectories on a discrete time grid. Then, okay, so does by consistency imply the same thing? Can we conclude from, let's say, by consistency that there exists a master complex value measure on space of pairs of trajectories instead? Okay. And the answer is by consistency on its own is not enough. There are mathematical reasons why it's not enough, because complex value distributions need a little bit more. There's another condition, but we can already deduce now, because we saw Zeno effects specifically, because we saw Zeno effect, we can combine it with by consistency to actually prove that indeed there exists this master measure. Okay, it's tied to Zeno effect specifically. Okay, it's very much because, okay, by consistency is one condition you have to fulfill. It's like analogous to consistency for standard Kolmogorov extension theorem, which gives us this master distribution and whole trajectory picture. But in reality, there is also a bounding requirement for probability, those multi-time probabilities, which is trivially satisfied for probability distributions because they are positive number smaller than one, okay? But for Q, which are complex value, this bounding property is more trivial. And this boundedness is like, essentially, you have to show that a norm, this will be okay, just a teaser. Next week there will be more. That you take a norm. It's kind of technical, but I think it's kind of it will be useful, because I want to really show how it's tied to Zeno effect. Zeno effect is a manifestation of this, but also it's interesting. Okay? It's interesting, and this norm one, as it's called, it's defined as a. Yeah, there are. Oh,
well, I know that many norms, but usually you use only one.
No, it depends what functional analysis. This stuff measured. There are actually use cases for many different norms for different reasons. So the norm is almost like normal norm, but you have to have because Q is complex value, you're taking absolute value. Okay, so for standard probabilities, this is trivial. This is just one, because standard probabilities are positive. Absolute value does nothing, so it just turns into norm one, turns into just normalization, which is one. So it's trivial, nothing to see here. But here we have normalization for Q, not for value, absolute value of Q. Okay, Q1, property Q1, normalization. You see there is no absolute value here. That's a big difference. That's a huge difference. Okay, now showing that, and essentially the second requirement for having this existence of this master measure is by consistency, plus this kind of norm has to be say supremum. So no matter how dense you take the time arguments, no matter how many time arguments are there, okay, so this no matter how large n is, this will be always finite, okay? So this is like a bounding, uniform boundedness condition. For And let's write it like that. It's not very precise. Okay, next week I will make it more precise if we need. But this is the essential gist. Okay, because the essence of this extension theorem, both for classical and for in this case for quantums and the probabilities, is like if you have this distribution on space of whole trajectories, and trajectories for all times defined, right? If you have this, then of course it's very trivial to like sample on a time grid, right? So having these multi-time probabilities coming from this master probability distribution is trivial, right? But the other way around, which is the contents of extension theorem, it's like, so you have your discrete time probabilities, and you want to say, okay, what happens when I start to make the grid more dense? And is the limit where I make it so dense that it's actually whole real line? Does it make sense? So, samples, discrete time samples of trajectory, can I make them in some limiting process to whole trajectory? Okay, does it make sense? So essentially you are asking, is time continuous or is time discrete in my theory? Okay, that's like the fundamental thing that you are answering by checking for this extension theorem. So of course, in a classical world, we know what the answer is. Its time is continuous. Whole trajectories exist. And here we are asking essentially the same question. Can sequences be made into trajectories? Okay, does this limit exist? Okay. And to get this, you have to be able to make it, the time grid, you have to make it more and more dense while nothing is blowing up in your face, okay? And this bounding condition, this is what makes sure that nothing will blow up, okay? And this bound, you can actually calculate this bound. It's a known value. And I guess we will do it next. So if you can show this bound, what is this value that's not infinite? That's enough to prove that existence of this master measure. And next week, I want to show that this bound, it actually is given by the stuff we got from Zina effect. Oh, you see this guy, this little fellow here, right? From Zina effect, we got to get Zina effect. You have to have this kind of second order, right? This coefficient here. This coefficient it comes back, and this is what gives you the bound, actually. All right? So it's like, if there was no Zina effect, the time would have to be discrete. I think you can push it even that far, okay? So it's like necessary to have, because we are accepting discrete time is very problematic. There's a lot of problems. If you would have to be forced to live with discrete time grids, that would be super problematic. There are a lot of difficult questions you would have to grapple with if that was the case. So you don't want that. You want to have a time to be continuous. And to have continuous time in quantum mechanics, you have to have Zina effect. That's what I'm saying here, really. So it's all connected, and it's so fascinating. And we'll talk about this. And of course, there are,
It's funny with the Zina, it's a bit of an off, but it's funny with the Zina effect that he focused on in a context of something that was wrong at that time.
Yes.
And now it comes back in a quantum mechanics where it is true, actually. Like,
yes.
Very, very the same, actually.
Yes.
Phenomenon occurs. But...
Yes. It is super funny. Or maybe Zeno knew what he was doing. Maybe he was thinking about quantum Achilles. And
he didn't know that's called quantum.
Yeah, he just forgot to quantify that it's a quantum. They didn't have this word yet, right? Of course, Achilles is a demigod. He's not classical, obviously. So he's quantum. And the turtle, he would battle some magical turtles. It's also quantum. Obviously. No paradox here. It's just observation of Zinn effect. You know, he knew B trajectory picture, you know,
and there were
1,000 years ago. Yeah. So that's yeah. So we have to finish it here, and next week we will elaborate on this B trajectory picture. We have our properties, we have our B probabilities, and we will, you know, first conclusion would be this B trajectories which were teased throughout the lecture all the time, right? But I will expose it to you for your inspection fully next week. Unfortunately, I cannot do it this week. Yeah, there will be a lot of. It's super interesting. And you know, it's not the end. There are a couple of more lectures still. B trajectory picture doesn't finish everything, but it finishes lecture for today.